Hello, welcome. So, in the previous episodes, we got this computer running on a new instruction set architecture um, that is, well, hopefully the final one that we'll need to implement in order to get this computer fully working. So, in this episode, I'd like to move us a little bit closer to having conditional logic or conditional branches, essentially. In order for this computer to be fully Turing complete, we need to be able to make decisions. And currently, the only decision that we can make is to emit these halt and error lines when we execute a must-seek instruction. But I'd like to move us towards proper conditional logic. So having a bit that we can use to decide whether or not we jump. Now, I was looking through the processor as it currently is, and I was noticing a bit of a problem. The decoder is doing too much. I'm sure you probably noticed that in the previous episodes where this was getting more and more complicated, but there's two concepts that are conflated here. So the first concept is understanding what the instruction is and extracting the information from it. And that's what a decoder's job is. So I think that's fine. But the other thing that it's doing is figuring out how to execute. For example, we've got it figuring out what a jump instruction is and providing that as output. And even in here, there's a bit of a conflation going on. I mean, determining the opcode does make sense from the format, and maybe it does make sense to do some of this stuff, but then we might want control over this in other places of the processor. And I think that's what it comes down to. We want to control the processor from a central place. And right now, control is kind of distributed. There's a bit of control in here. There's potentially a little bit of control down here. And if we look in the execute unit, there's some control going on down here potentially, where it's looking at the opcode and it's deciding whether or not it's a must-seek instruction. And I mean, you could debate it, but it's also interpreting the opcode here to determine what the result should be. So there's just a bunch of places where control is happening, where a decision is being made as to exactly what to execute, and it's potentially going to be a lot better in the long run if we consolidate that into a single place. And I feel like now it's a good time to do that, because as soon as we add in conditional logic, that is conditional branches, we're going to get a lot more complicated, because now a decision has to be made whether or not that jump is taken, right? And if the jump isn't taken, we want to make sure that the program counter doesn't get the new value. And we could add that fairly easily right now. We have a jump here. We could add in like the condition, but then we have two conditional jumps and we have two non-conditional jumps. So we have to make a decision on whether or not we're in a conditional jump, and then we need to decide whether or not to take that jump. So I think the first thing that I would like to do is pull this out of here and start building a module that handles that logic. And I think that module should fit right here potentially. But first things first, of course, let's create a embedded circuit for it. And we're going to save it as control. Let's put this in here and this would be the ideal place for it, or maybe a little below. But we got wires running through there, so let's see if we can fix that. I'm gonna copy this into there as well. So then op is just gonna go straight through. Okay, so this still works, which is good. I feel like there's a bit more that we can do to clean this up. So how I intend this to work is to have a T bit that'll come from the execute unit. So let's add that. Where should the register for the T bit exist? We want to remember what the result was from the previous instruction. So where should that be? I guess we can put it here for now, and if it doesn't belong here, we can move it. So if the top 3 bits are this, then it's definitely a jump. We want to check if the bottom 2 bits, the most significant of those 2 bits, will indicate whether it's a conditional jump or not. And then the bottom bit will indicate whether we want T-bit to be true or false. So that's kind of the logic we need to do. Let's see if we can figure out how to do that logic. So the bottommost bit will invert or not the result of T. So that part is easy. I'm still trying to think of how to do the jump part. So I think this will work. I guess we should try it out and see. So it wants this bit set, and then it's jumping. And then if this bit is set, then it won't jump because it's expecting this to be true. But if we make this true and clock it, then we will jump. But then if we set this, then we won't jump again until this goes low. And then now we'll jump. But if this is low, then we always jump. I believe that is correct. I wonder if we can clean this up just a little bit though. So I'm not sure if this is the best way to do it, but it does reduce the number of levels of logic, so maybe it's fine. But yeah, this does everything that we need it to currently. So now we just need to get the execute unit to produce the T in bit somehow, and then wire it all up. Okay, I think that's working. So the next thing that we need to do, and by the way, I plan to actually get rid of the halt and error lines here. Likely what would end up happening is that would probably be handled in the control. So what we would do is instead of having a must eq instruction, we'd have an eq instruction that can check if 2 things are equal. And then if you halt immediately after, it'll either raise the halt line or the error line, and then our tests will continue to work. It's just we've replaced the mustique instruction with a halt and a conditional check. So then I guess we need to implement the new instructions that we have in our assembler. So we have an eq instruction, and we also have a few kinds of jump now. Well, I think we should test this out in the Fibonacci program as well. There we go. So here we're going to check if it's the number 13. If it is, then we branch back all the way to the top and we kind of reset. And we should probably add in instructions to fully reset. Let's see if this works. It does not, because our 13 is in R2, not R3. Or did we actually? No. R3 gets zeroed out. So there's some oddness. But one of the oddnesses is we don't have the new instructions being displayed in our display. So that might be useful. Let's do that. Okay, we've got our equals instruction. Now we have BRT to 0, but the jump line is not high. And then we have our jump to 2, which we do. And the next one. So our eq is changing R3, I think. Yeah, that's what the problem is. How would we fix that? And also, what would be a better value? Yeah, I think 8 probably. Oh, we didn't recompile. That would do it. Okay, so we can see that the T-bit is working, and it is emitting a high signal here. It goes into here. We can't see the T-bit actually being displayed. Perhaps we can fix that in a moment. But if we advance one more, then we can see that the branch is now being taken. So the jump line is high because the previous instruction detected that 8 was in this register. So that's pretty awesome. We now have conditional logic. It is a very large milestone. So that's pretty cool. All right. And we can see the T-bit here, and there it is. It's true. So branch if true, and we get the branch. So I think it makes sense to also tack on to this video getting rid of the mustique instruction and converting that to halt instruction. And then we can continue to have the error line, but it will go, this logic here would probably go into the control module that we've just built. That's probably a better place for it. So let's do that now. We might as well complete this feature. So the halt instruction is actually a sys instruction, and we're not emitting that information yet, so we need to do that. So I'm thinking, maybe sys overrides with a different set of these? I'm not sure. Okay, so we need to figure out how to integrate the sys line here into a couple of different places. We want this to emit a NOP in the case that sys is high. So I guess we could add a line to this. Right. So we should have failing test cases now. Oh, and we've got several problems. All right. All right. Okay, that's a little bit better. Okay, just the test suite is failing, so we can fix that fairly easily. So the halt instruction should be just 1. All 16 bits are 0 except for this one. I think that should work. That seems to work. So the tests are still failing. I'm not quite sure why. Oops, hold on. So run tests. What's going on here? The halt line never goes high. Okay. I think this is the culprit here. Yep, there we go. Cool. We're still getting problems. Halt line is still not going high. This should not be a jump. So this is 0. Yeah, and it's a sys instruction. Oh, I think I know what the problem. Yeah, jump is 1. This is 0, but the 1 goes in this field. So the third bit should be 1. That's what the problem is. Yes, that did indeed work. Excellent. Excellent. Now both tests are passing. Awesome. Awesome. Everything is working. All right. So we now have a computer that is fully working. We're able to conditionally halt or error depending on the value of the t-bit, and we're able to set the t-bit as part of our execution. So this is not quite Turing complete yet because we need access to an arbitrary amount of memory, but we do have the ability to conditionally branch, which is one of the requirements for Turing completeness. So this is pretty awesome. So yeah, thank you very much for watching. I hope you have a great day. Bye.